Okay, this is 8-5, Trig Identities. So this lesson is just teaching us sort of relationships that happen within the trig functions, which help us to sort of transform trig statements, I guess, into ones that are easier to deal with, which we appreciate. So we're going to talk about a couple different what we call identities, which just means things that are the same. And then we'll talk about how we use those to transform different sentences, basically, that involve trig functions. So the first is the complementary identity. This identity says that if you take sine of some angle, it's equal to cosine of 90 minus that angle. It's called complementary because this theta and 90 minus theta are two angles that are complementary to one another. This happens because I just want you to imagine with me two of like these both are the same triangle. Okay, we're going to assume that they're the same ones. And we're going to say that this is like, maybe it's a 30, 60, 90. Wait, that's the wrong one. Maybe it's a 30, 60, 90. 60 and 30. And this side is like 4, and this side is 8. Okay, so just say with me, we are going to find sine of this angle here. Ooh, sine of 30 right there. So that would say sine of 30 degrees is equal to opposite over hypotenuse. So that's 8 over 4. And then say we wanted in the same triangle to find cosine, that was meant to be a highlighter, cosine of this angle, 60 degrees. So cosine is adjacent over hypotenuse, so cosine of 60 is now 4 over 8. So do you see how if we take sine of one angle and cosine of the other angle, the fraction ends up being the same here? And notice that the angles that we're taking them here, 30 and 60, maybe I'll highlight in the right color, 30 and 60, those two angle measurements are complementary, meaning they add to be 90 degrees. And that's just because any two angles in a right triangle, so like we already have a 90 degree angle here, and so to make 180 we just need 90 more, which means that those two angles in a right triangle are always going to add to be 90 degrees. And so that's why this is true. It just means that we're just looking at sort of the same values, but using different trig functions and the complementary angle to find them. So anyway, sine of an angle is equal to cosine of the complementary angle. Maybe I will highlight this in blue instead so that we can tell what's happening here. There we go. So that is the complementary identity. Quotient identity is just, it's actually really related to what we just did with tangent and the unit circle. Tangent is a ratio of sine over cosine. So tangent of some angle is just equal to sine of that angle over cosine of that angle. And that's just always true. Sine over cosine is tangent. And so we are going to use this, mainly this identity, to transform some of these statements here. So how this is going to work here is we have this statement here and this statement here. Our goal is to connect these two statements with some logical points between them that prove that they're equal. And it might not take that much space, but we're leaving that much space just in case, okay? So cosine over sine is exactly the opposite of sine over cosine, right? It's like upside down. So for example, if we did one, cosine over sine is the same thing as 1 divided by sine over cosine. Because when you divide by a fraction, you multiply by its reciprocal. So we're just saying that 1 divided by sine over cosine is the same thing as cosine over sine. So that's true, because we're trying to get to 1 over tangent here. And so 1 divided by sine over cosine, this statement here is equal to tangent, right? 1 divided by tangent of theta. Those two things are the same, which we can rewrite as 1 divided by tangent of theta, which is where we wanted to get to down here. So those two statements are the same. Cosine over sine is the same thing as 1 over tangent. And I'm not going to be super specific about how you get between these two things. Like, you could also have seen that this is just the reverse of tangent, and so you could say that it's just 1 over tangent. Like, there are shorter ways and longer ways. It's kind of up to you how it makes the most sense. Your goal is just to connect these two things with logical arguments for how they're the same. So, sine of theta plus cosine of 90 minus theta is equal to 2 times sine of theta. So, I will just point out here that we have the complementary identity going on here. Cosine of 90 minus the angle is the same thing as sine of theta, right? That's what this says. Sine of theta is the same thing as cosine of 90 minus theta. So this becomes this, and we still have this plus sine of theta over there. And when we have two sines of theta added together, there are 2 sine thetas. And that is what we wanted to get to down here. Good, so hopefully that made sense to you. Now we have tangent times cosine. So I'm going to notice here that tangent is equal to sine of theta over cosine of theta. Just like that, and we still have the cosine of theta happening there. So we transformed tangent into that one using the identity, quotient identity, that's what I'm trying to say. And now that we have this, we notice that we are dividing by cosine and multiplying by cosine, which cancels each other out, and we're left with just sine of theta, which is what we wanted to get to down there. So hopefully these are making sense to you. We're just trying to transform one statement with trig functions into another using these identities. Let's add one more identity. This one's the Pythagorean theorem identity. The Pythagorean theorem identity is just based on the this triangle inside of the unit circle and Pythagorean theorem. That's why it's called Pythagorean identities. So what's happening here is, remember we have the hypotenuse of 1 in the unit circle, and that cosine gets us this side and sine gets us this side. So if we were to use Pythagorean theorem, which we can because it's a right triangle here, that says a squared plus b squared equals c squared, and just replace all the things that we know, this would be like cosine of theta, this would be like sine of theta, and this is like 1, right, because the hypotenuse is 1. But 1 squared, 1 times 1 is just 1, so we're left with this, cosine of theta squared plus sine of theta squared is equal to 1, and that is the Pythagorean identity. It just says that if you square cosine and sine of the same angle, you end up with 1 no matter what. And this leads to some other identities. That's why we say identities. That's just because we can transform this statement by like subtracting sine squared of theta on both sides, or subtracting cosine. So you can, all of those just come from this statement. So essentially this is the Pythagorean identity. I will mention also that for some reason with sine and cosine, it's conventional to put the squared in between the cosine and the theta, like this. Truly, there's really no reason at all to do that, except for that maybe it looks better. But these two things are equivalent, like this cosine of theta squared and this cosine squared of theta are the same thing. It's just written with the squared here instead of here, which really, I don't know why, but that's just conventional. So you might see this, and that's the same thing. So let's do some more of these proofs here. We're gonna use sort of a combination of all the things that we have so far. So cosine times 1 over cosine, we're supposed to say is 1. So cosine times cosine 1 over cosine is the same thing as like, oops, wrong color, is the same thing as cosine of theta over cosine of theta, like this, which is just 1, right? Something divided by itself is always 1. So that one's super easy, right? But sine, now we have sine of theta times cosine of theta. So sine of theta over cosine of theta, which is what that fraction becomes. That is the same thing as tangent of theta, if you remember from the other side. Sine over cosine is tangent, which is what we wanted to get to. Now we have tangent over sine. So what I'm going to do is I'm going to split up, instead of putting them together like I have been, I'm going to split this up to be tangent of theta times 1 over sine of theta. And then I'm going to transform tangent into sine over cosine. So the same thing. And when we have that, we notice that we have a sine on the top and a sine on the bottom that cancel, which give us 1 over cosine of theta, which is what we needed. Awesome. Okay. This one I'm going to do the same thing. I'm going to take tangent and I'm going to replace it with sine of theta over cosine of theta. And this is still times cosine of theta. So those two are the same. We now notice that we have a cosine on the bottom and a cosine on the top, which means that we just are left with only sine of theta on the top, which is what we wanted to get to down there. Now we have sine of theta over tangent of theta plus 1 over cosine of theta. So first of all, I'm going to separate these out a little bit. I'm going to do sine of theta times 1 over tangent of theta times 1 over cosine of theta. Now that it's split up, oops, I don't know why I just equaled 0 there. This value here is the reverse of tangent. It's 1 over tangent. So instead of writing like sine over cosine, it would be cosine over sine, because it's flipped upside down, essentially. So these two things are the same. And we're multiplying that by sine of theta and 1 over cosine of theta here. So notice that the cosines cancel. I will grab a different color. There we go. And so do the sines. And so that means that all we're left with is just 1, which is what we wanted to get to there. Last one, number 6, we have 1 minus cosine squared of theta. So I'm trying to remember what I was going to do with that. Oh, okay, so it says I'm going to replace, this is kind of funny, but I'm going to replace 1 with, using my Pythagorean identity, I know that 1 is equal to sine squared of theta plus cosine squared of theta. So I'm going to replace 1 with sine squared of theta plus cosine squared of theta, and then we still have that minus cosine squared of theta going on. So this is the 1 that we just replaced. And then we have cosine squared of theta minus cosine squared of theta, which just equals sine squared of theta, which is what we wanted. So this is another version of the Pythagorean identity, that 1 minus cosine squared of theta equals sine squared of theta. So you might see them in different ways, but truly they all come from just this identity that we have. Good. That's all I have.